Now we'll go through the section, Landform and Vegetation Effects on Climate. The climate of an ecosystem is not driven just by global to regional processes. The local state factors and interactive controls are important in determining climate. Here we'll cover how factors such as proximity to water, topography, and vegetation also influence climate. The authors state that the spatial distribution of land, water, and mountains modify the general latitudinal trends in climate. So what they're saying is that when you want to understand the climate of a place, you can't just know what its latitude is. There's a lot of other factors that go into determining that local climate. For example, land surfaces can impact climate. An example that they use in the book are the monsoons. So earlier, the authors had showed that different patterns of low pressures and high pressure systems that would set up typically at January and in July. And we're going to focus on one right now, and that's the Siberian high that gets set up in January. So here's the high pressure system that often gets set up mid-continent in Asia. And this high pressure system, as you remember, is descending dry air. It's dry times when that high pressure system sets up over Siberia. In contrast, in July, in that same region, there's a low pressure system that gets set up. Unfortunately, Asia gets split up into two sections right here, but that low pressure system gets set up north of India over the mid-continent. And that means that's going to be sucking air up into the system. And you can tell that it's sucking air up here and here. And that's going to be relatively warm oceanic air. Now, the differences in the high pressures and low pressure systems that get set up over the Indian subcontinent, over the central part of Asia, at the continental scale, really drive the pattern of rains. So, for example, in the summer, this land here is going to heat up a lot more than the warm ocean. So the ocean over here is relatively warm, but the land heats up a lot more. And the differential heating causes air to rise. That sucks up relatively moist air coming off of the ocean that then rises as it hits the highlands. Clouds form and rain falls. That air cycles back to then pick up more moisture and bring that on land again. And this generates the summer monsoons. In contrast, in the winter, as you know, over that region, there was a high pressure system. And that high pressure system tells you there's descending air. And that's caused again by differences in temperature in the ocean, which is still relatively warm, and the land, which gets pretty cold. And so now you've got warm air that rises over the ocean. The rain falls back down, and then dry air descends over the land. So the differences in heating between the ocean and the land can cause seasonal patterns in rains. Now those patterns that we see on a seasonal scale, we can also see on a daily scale with what are known as land breezes and sea breezes. This is the other half of the figure that they show in the book, and it's really just the same pattern, but it's on a daily scale instead of an annual scale. So on a daily scale, if you're next to the ocean and the water is relatively warm enough to have enough evaporation, that during the day, the land heats up more. So if this is our ocean and this is our land, during the day, you get heating and rising of the air. This is going to suck up air that's relatively moisture laden. It rises, and then usually about midday, sometime in the afternoon, clouds form and it rains. This air cycles back to close the loop. During the day, the pattern of heating is different. The land cools off enough and the water is still relatively warm. So you have your water, you have your land, and in this case, you get rising here over the water, descending air over land, and then this is the land breeze. As air is now, as the winds are now shifting from the land to the water. So we have day sea breezes and night land breezes that are causing afternoon thunderstorms, and then relatively dry open skies during the night. Here's an example of some of these breezes. This is would be the land breeze. So where we are in the world, This is the Arabian Sea, this is the Bay of Bengal, this is the tip of India, and this would be Sri Lanka here. The distance right here, just for scale, is somewhere on the order of 700 kilometers. So that's pretty big parcels of land that we're talking about. And you can see, if you take a look, that there's a ring of clouds that formed adjacent to the land, with an area that's relatively cloud-free right adjacent to the land. And what this is that this is relatively descending air that's then cycling out over the waters and pushing those clouds out. The air rises and clouds form, but not over land, instead over the ocean. Now, in addition to these patterns of at the land-water interface, we also have what are called orographic effects. So here's a mountain, for example, and when you take a look at the patterns of clouds around the mountain, we're going to have air that's rising up for one of two different reasons, and then clouds form right around here at the tip of the mountain. And this is not atypical, and it depends on the general pattern of the wind and the patterns of heating around the land. But if you get breezes that come up, pulling moisture up the mountain, as the air rises and gets cooler because it expands, you're going to have condensation, you get clouds form. And that's a pretty typical pattern. Now, in addition to having patterns around an individual mountain, we also can generate rain shadows due to orographic effects. And here's an example where, again, we have a source of moisture. This is an ocean that's relatively warm, and then as the prevailing wind goes across that ocean, it's going to pick up moisture. Now, it's not going to drop that moisture yet until it cools, and that doesn't happen until it rises in elevation. And as it rises, the temperature is going to drop. So it's 20 degrees down here, 7 degrees up here at 2,000 meters, and by the time you get up there, you'll have condensation, the clouds form, and they'll drop their rain. But they only drop their rain on the windward slope. As that prevailing wind goes up and over, it's not going to carry any moisture with it. And then on the leeward side, so on the opposite side of the prevailing wind, it's relatively dry. And this area right here is known as a rain shadow. So there's a secondary effect associated with mountains that can make it rainier, wetter climate on one side and drier on the other. So this warm air rises, drops its moisture, and then it goes over. It's cool air that's descending. That's relatively dry. These rain shadows are pretty typical of relatively large mountain ranges. This is a photo of the Great Basin, which is located in the western part of the US, and prevailing winds in this case would be coming over the mountains, drops of snow, and then as it comes back down on the opposite side, so we're probably looking west here, that this area is relatively dry. So it's wetter on the western side, drier on the eastern side, for example. And this causes big spatial variation in climate. Another example of a rain shadow can be seen here. This is the big island of Hawaii, and we get trade winds that come off of the Pacific in this direction. So these winds are coming off the Pacific, hitting land, and then this is a big mountain ridge right here. And as it hits the ridge, it's going to rise up and it's going to drop all the moisture on this side. And you can see that this area is forested, it's a lot greener. And by the time that comes over the hump and down, that area is relatively dry, and as it descends, it's not necessarily going to drop more moisture. And so this part on the leeward side is a lot drier. So lastly, we talked about some of the landform impacts on climate, but vegetation also impacts climate. An example that they give in the book is differences between the patterns of energy and water exchange that happen over a rainforest in contrast to a pasture. And you can see that there are differences in albedo, surface temperatures, and evapotranspiration that happen. So high latent heat loss over rainforest vegetation, there's a lot of evaporation, which means more humidity goes into the atmosphere, more of that energy goes into evaporating water, and you're going to get precipitation from the evapotranspiration. So we have differences in sensible heat loss, a lower albedo, lower surface temperature, but more of that energy going into evaporating water. When you're over a pasture, relatively bare ground, there's lower evapotranspiration compared to the forest, higher surface temperatures, and higher sensible heat loss. So more of that energy goes into making the air warmer than it does evaporating water. And as a consequence, we have less humidity and recycling of water and reduced precipitation. So these are examples or contrasts where you're going to get differences of precipitation over two areas just by the type of vegetation you have and how much evapotranspiration that you're going to get. Here's another graphic that shows the same pattern. When we're on relatively wet soils, vegetated, you're going to have high latent heat flux, lower sensible heat flux for a given amount of radiation. In contrast, on a dry soil or soil that isn't quite as vegetated, you'll have a lot more sensible heat flux, not as much latent heat flux, a taller boundary layer, less evapotranspiration, less precipitation. So in summary, when we want to think about the climate of an area, it's more than just thinking about its latitude. We have to think about the proximity to water. We need to think about the arrangement of the land, the topography, changes in elevation, in addition to the vegetation that's there. And all of these factors come in to affect the climate that's there. So although we think of climate as a state factor, that climate is not necessarily independent of other state factors and can be regulated to a certain degree by the vegetation. So climate is relatively complicated. There's a lot of factors that go into that. But each of those can be broken down when we're starting to take a look at individual ecosystems to understand the climate of that ecosystem better.